Given this circuit, we're going to calculate the complex power. Before we do that, it's useful to review some of those rules. For example, in direct current, power is equal to a voltage times a current, which is also equal to I squared R, or E squared divided by R. It's the same thing for AC. Here we see the vector S, complex power, is equal to the voltage vector by the complex conjugate of the current vector. It's also equal to a current squared multiplied by the impedance, or a voltage squared divided by the complex conjugate of the impedance. We have to be careful though, because this current is the absolute value of the current vector. Likewise, this voltage, which I should have done as a V here, my apologies, is the absolute value of the voltage vector. At this point, it's useful to review our power triangle. Here we have S on the hypotenuse as volt amperes. We have P as real power on the base as watts. And we have reactive power as Q in volt amps reactive. As we start working on this problem, it's useful to break it into chunks. For example, here's impedance 1. We'll call this impedance 2, and we'll call this impedance 3. And one more. In teal, we're going to circle this thing, and we're going to call this the impedance of the box. So again, the impedance of the box is Z2 in parallel with Z3. We solve for the impedance of the box using our formula for things that are in parallel. When we're done, we find out it's 4.1 plus J 1.9. We can calculate the total impedance as impedance 1, which is 0.1 plus J, plus the impedance of the box. So that gives us 4.2 plus J 2.9. While we're here, let's go ahead and calculate the total current, which is the source voltage divided by the total impedance, which gives us about 41 amps at an angle of negative 34. From here, the impedance of the box may be calculated. From here, the voltage on the box may be calculated using the voltage divider rule, where we have the impedance of interest, which is the box in this case, over the total impedance multiplied by the source voltage. And when we're done, we find that the voltage on the box is 184 volts at about negative 10 degrees. Just to keep track of where we are, we're going to go back up to our original picture and we're going to write these values in. So here's 41 amps at an angle of negative 34. And the voltage on the box was 184 at an angle of negative 10. At this point, we can start working on our power. Now remember, power is a voltage times the complex conjugate of the impedance. So we can calculate total power as 208 multiplied by that 41 at negative, correction, not negative, it's positive 34, because we need to take the complex conjugate. It's a classic mistake. People mix that one up all the time. Solving for total power, we see that it's about 7 plus J5 kVA. Or if you prefer, in polar form, that's 8.5 at an angle of 34 degrees. Personally, I find it useful to put the power triangle into these problems. Here we have 7 kilowatts as real power, 5 kVAR as reactive power. The angle is 34 degrees, and then the hypotenuse here is volt amps, and that's 8.5 kVA. Power factor is another useful thing to calculate. Recall that power factor is the cosine of theta. In this case, that's the cosine of 34.3 degrees, which yields about 0.83. People will often express this as a percentage. So we might say that this is 83%, and then we'd say it's inductive. It's important to specify which, because power factor in and of itself does not tell you if the circuit is inductive or capacitive. At this point, we could call the problem done, but there's one more thing I'd like to show you, and that is if we took the total power and then we compared it to the individual powers, what would we find? Well, what I'd like to show is that the total power is equal to the summation of the individual powers. As we go along, remember our formulas here, where complex power is the voltage times the complex conjugate of the current, or the current squared times impedance, or the voltage squared divided by the complex conjugate of the impedance. Again, where the current and the voltage are the scalar parts. They're the absolute values, the same thing you would read if you were using a voltmeter. To get started, we'll calculate the complex power of impedance 2, because I think that's one of the easier ones to do. We calculate that as a voltage squared divided by the complex conjugate of the impedance. Don't forget, it's negative J5 here because we need the complex conjugate. Solving for that, we see that impedance 2 is 2.7 plus J 1.4 kVA. We solve for impedance 3 in the exact same way, yielding 4.1 plus 1.8 kVA. Impedance 1 needs a little bit more work. One way to solve it is to figure out what the voltage drop across it is. So the voltage across impedance 1 is the source minus the voltage of the box, which gives us 41 volts at an angle of about 50 degrees. With that, we can use our voltage by complex conjugate of the current formula, which gives us 0.5 plus J 1.8 kVA. Now, you remember this piece where we said that the total complex power was equal to the summation of the individual powers? Well, that's what we're going to do now. Here, we underline in purple the real component for each of the three powers. We're going to take the summation, that's the sigma symbol there, so we're going to take the summation of the real pieces, which is about 7.3 kilowatts. Now, we examine the reactive power, and we sum that up as well. So we end up with 7.3 plus J5 kVA. And if we go back to that first power triangle we drew, that looks really familiar. So this is one way of showing that the total power is equal to the summation of the individual powers.